So as you take a look at this problem, this is the sort of thing we're going to be looking at today, and really is going to be the theme of this week. We're taking what we have been doing with solving systems of equations, and we're going to be extending that into what are called 3x3 systems of equations. It's called a 3x3 system because you'll notice that there are 3 equations, and there's a grand total of 3 different variables, hence the 3x3 thing. And so a lot of the methods that we've been using, a lot of the methods we were using last week are still going to be coming up. They're still going to be relevant here as we go forward. Now this first one, this is what I might think of as perhaps the easiest type of these. If you were taking a look at solving this without even being told any special skills or techniques or anything, what do you think you would do first? Yeah, that first equation is set up beautifully, right? We can solve that first equation, 2y equals 12. So we could take that and we could solve that for y. Okay, so we divide both sides by 2, and then we find out that y equals what? All right, I now know that y equals 6. Cool. Now what can I find? Again, without even knowing any special skills, what can we go ahead and go on to next? Yeah, notice the second equation has y and just one other variable in it. And so I can take what I know y is and plug it in there. Now this one we'll probably have to write out a little bit more to be able to see it. So we're going to do 7x minus 10 times the 6 equals negative 25. And then we're going to solve that through. And so when we work that through, we end up being able to find that x is 5. And again, be showing all your work as you go through this. Like on mine up here, I didn't show like plus 60, plus 60. Why? Because I'm trying to make you not have to sit there too long as I go through just writing it up there so we can see the basic process. But you still should be putting this part down on your paper as you go as well. So we now know that x equals 5. I'm still not done with this problem though. What am I going to do for my last step? Yep. Notice our bottom equation is the only equation that includes the z, which is the only thing we have left to solve for. I already know the x, I already know the y, so plug the x and the y into that last equation and figure out what z would equal, please. All right, so we plug in the x, we plug in the y, solve that for z, and then when all is said and done, you should have found that z equals a negative 3 here. And then we're done. This is the sort of thing we're looking for. Now, you'll notice here that I've written my answer as x equals y equals z equals. In our previous systems that we've been solving, I have actually written it as coordinate pairs, ordered pairs. Can you do that with this? Could we write it as 5, 6, negative 3? Is that actually a possibility? Is that a thing? It technically actually can happen. But I'm not going to necessarily recommend it because this is such a foreign way of us looking at it. We tend not to work in 3-dimensional coordinate grids that I would say, no, don't worry about it. But just so you know, technically you can, but I would prefer if you just say what x equals, y equals, and z equals like that. And I just want to go on one other little tangent here. When we solved our systems of equations, our 2x2s that we were doing last week, remember that our solution represented the coordinates of a point where the 2 lines, if we graph the 2 lines, it would graph the point where those 2 lines crossed, right? So if I have 3 equations, what does the solution represent then? It actually still represents the intersection point. It's just that, and I'm going to have to find a graph that can help us visualize this at some point, but it's just that when we graph equations that have 3 variables in them, like this one, if I graph that, it's not actually a line. It's a plane in 3-dimensional space. And so if you think about taking 3 planes and like having them intersect, if you take 2 planes, bring you back to geometry here, if you take 2 planes and have them intersect like 2 pieces of paper, they'll intersect and form a line at all those points where they intersect, right? The third plane, which is why we need a third, then crosses over that line of intersection and creates the actual point of intersection, which again is why there's just one solution here. Moving on to our next system that we're going to solve, please go ahead and write down this one, and then think about what you might be doing to start solving it. And once you have it written down, again, be thinking about how might you go about solving it. And I'll give you a hint on this. I don't need to give you any new or special strategies. You actually have all the tools to be able to do it already. If you just maybe start walking it through, you might even figure out what that is. I mean, give it a try first before we start doing it together. So as I take a look at this, the very first thing I would do is the same kind of thing I did in the last one. And that is, because I have one equation that just has one variable in it, I'd start by figuring out what that 1 equals. I can start by figuring out what z is. And so if negative z equals 14, I'm going to divide both sides by negative 7. And so I know then that z is negative 2. I know that right off the top. But you'll notice that neither of the other two equations has just z and one variable. They both have two variables in them. But I could still plug it in. So let's take a moment and see what that would look like. If I take the negative 2 and plug it in for z up here, you end up with this if you plug in the negative 2 for z. And then seeing that, I see something I can simplify. So I'm actually going to try to simplify each of those equations, because I can actually multiply by the negative 2 and all that kind of stuff. And so I multiplied through by the negative 2, and you notice what this is starting to look like. This is starting to look like those problems that we were doing last week. The only difference is that we have this extra number over here on this side. And while we actually could still use the same methods that we used last week, even with that number there, I have a feeling we're going to be more comfortable if we go ahead and get rid of that. And so I'm going to take this first equation, and I'm going to subtract the 10 from both sides of that first equation. And then I'm going to go to the second equation. I'm going to add 4 to both sides of that second equation, so that I just have the x and y on the left side and just have my numbers over there on the right side. And having done that now, we now see a system of equations that looks just like the stuff that we were doing last week. In fact, it's a fairly easy one to do, like we were doing our stuff from last week, because I see elimination method. And again, I know it's elimination because they're both in standard form. You know, the x and y are on the same side there for both. Everything's lined up. And so this is the one where I add them. Now, in this case, do I need to multiply one or both of the equations by something before I add them? No. Can I? Yes. But I don't have to, because I see I have a negative 6y and a positive 6y there. That means I could go ahead and just go straight away and just start adding those two equations together. And if I do that, I end up doing negative 3x plus 8x. That's 5x. The negative 6y plus 6y is 0. I always mentally check that. I always mentally check that it does add to 0. It helps me catch any possible mistakes. And then the equal sign. And then 9 plus the negative 14 is negative 5. Well, of course, all I got to do now is divide both sides by 5, and I know that x equals negative 1. All right, so now that I know that x equals negative 1, how do I find y? Yeah, it's the same as the elimination method that we were doing last week. You just plug it in. And so take your x value, plug that back into one of the original equations. Actually, I wouldn't even necessarily use an original equation, because then I have to plug in the z again. I already plugged in the z like down here. I could take that negative 1 for x and plug it in right there. So I bet that's even easier. Let's do that. So I'm going to do negative 3 times the negative 1 minus 6y equals 9. And I could then solve that. So the negative 3 times negative 1, that's a positive 3 minus 6y equals 9. So I'm going to go ahead and subtract 3 from both sides. So negative 6y equals 6. Therefore, y equals negative 1. And this method that we just went through, this is kind of a little taste about what the harder types of problems like these are going to look like as we go through. Really what we're doing is we're just taking the stuff you did last week, and we're just seeing different ways that we can play with those same techniques to make them actually work with something that starts out as a 3 by 3, and just boil it down to a 2 by 2. Now, why do I want to make it into a 2 by 2? Because we start out with 3 equations and 3 unknowns. I then go down to 2 equations with 2 unknowns. And once I do that, I can get to 1 equation with 1 unknown. Once you hit that 1 equation with 1 unknown, that's what we can solve. It's just we're always trying to get rid of an extra variable. We're always trying to reduce that down. And so as you take a look at these types of problems, that's kind of a general theme going forward, is how do I reduce the number of variables that I'm having to work with at this time? So we're going to do just one more problem here together today. Go ahead and please write down this problem. So now we're taking a look at a different problem. And notice each of these that we've looked at so far have all been 3 by 3 systems. It's 3 equations and there's been 3 unknowns involved. And so it's just a matter of seeing how do we approach them. And remember what I was talking about with that last one. Our goal is really to get it down to be a 2 by 2, because if I can make it into a 2 by 2, then I can make it into like a 1 by 1. That is 1 equation with 1 unknown. Well, in this case, there is nothing that I can solve for immediately. I can't figure out what x, y, or z is right off the top. But of course, we are trying to make it into a 2 by 2, right? Notice we have a 2 by 2. No. Those first 2 equations are a 2 by 2 system in and of themselves. Each of those equations represents a line that we could then graph and solve. Of course, we don't need to graph it. We can solve it using elimination, but we can actually figure out where those 2 intersect for both the y and the z values. So please take that as a little system unto itself and solve it to find y and z. All right, so when you end up solving that 2 by 2 system that we had there at the start, you should end up with answers of y equals 4 and z equals -6. Just by solving it using the same techniques that we had from last week. And so notice what you're doing as you start one of these problems is you have to strategize a little bit, because each of these have used a different strategy. And you're always again looking, turn the 3 by 3 into a 2 by 2. And then you can figure out what one of them equals. All right, now that I found my y and my z, I still need to find x. Well, notice we haven't touched one of the equations yet. In order to solve a 3 by 3 system, you will always have to use all 3 equations. It's impossible to solve a 3 by 3 without using all 3. And so you know then that you're going to have to use that last equation. Well, as you probably already have figured out, you're going to take what y and z equal, what we already figured out from before, and you're just going to go ahead and plug those in for y and z, and then you can solve that equation for x. And so when we plug in and solve for x, you should have found that x equaled 1 there. And again, we're just plugging in at this point the 2 that we do know into one of the equations and then using that to find the last unknown, the one piece that we hadn't used yet. And so we get again our final solution up here of 1, 4, and -6.